Today we're going to talk about sampling and SNR, or signal-to-noise ratio, in MRI. In MRI, the image and k-space data domains are related by Fourier transform. The size of the image is described by the field of view, and the sampling, or pixel size, is labeled here delta x. In k-space, the dimensions of the patch of k-space that's required is often referred to as extending from minus kmax to plus kmax. Here we'll refer to the total dimension to kmax as kFOV. And the sampling spacing in this domain is labeled delta k. The sampling requirements for MRI are just a direct translation of the sampling requirements for the discrete Fourier transform translated into MRI units. So for example, delta k, the sampling spacing in the k-space domain, is simply equal to 1 over the field of view in the image space domain, if expressed in rotations per centimeter, or 2 pi over the FOV if expressed in radians per centimeter. And with perfect symmetry, delta x, the spacing in the image domain, is equal to 1 over the k FOV. You'll see this more commonly expressed as k max equals 0.5 over delta x, which is intuitively easy to understand, because at the edge of k-space, you have half of a phase rotation per pixel. Here's an easy way of visualizing this dependence of delta k on the field of view. So the sampling of data in k-space is a projection of the object onto the Fourier basis functions. For the discrete Fourier transform, the set of orthogonal Fourier basis functions is the set of complex exponentials that have an integer number of oscillations from one edge of the field of view to the other. So for example, if you happen to be sampling a point in k-space where the phase of modulation is 2 cycles across the field of view, you can ask where the next sample should be. Well, the next higher spatial frequency that will be orthogonal to the one you're at will be one where there's exactly 3 cycles of oscillation across the field of view instead of 2. And the difference between those k-space coordinates delta k will be 1 over FOV. So now let's relate these quantities to physical imaging quantities like the gradient and the sampling rate. So recall that k is gamma times the time integral of the gradient. For any small chunk of time delta t, delta k is just gamma times g times delta t. So this already gives you an expression that relates the sampling in k-space to the product of the sampling in time and the amplitude of the gradient. You can relate this in turn to the bandwidth of the sampling because the bandwidth is simply 1 over delta t. And if you like, to the field of view because delta k equals 1 over the FOV. Another intuitive way of thinking about the bandwidth is that it is the frequency difference between the spins at one edge of the field of view and the spins at the other edge of the field of view. And that's simply equal to FOV times gamma times g. And that's easy to understand because the quantity gamma g is just the gradient converted into units of hertz per centimeter. So that, multiplied by the field of view, should give you the frequency difference between one edge of the field of view and the other. Okay, so now moving on to SNR, or signal-to-noise ratio, in MRI. First of all, if the signal is filtered to avoid noise aliasing, which it is in basically all MR imaging sequences, then you actually don't even have to worry at all about the fact that the signal is acquired in k-space and transformed to image space. The SNR properties are exactly as though the signals are acquired from each voxel independently. So let's start writing down the expression for SNR. First of all, it sort of has to be proportional to the transverse magnetization, since that's what's generating your signal. That in turn has a complex dependence on the pulse sequence itself, including parameters like TE, TR, flip angles, and the local proton density. Those can be simulated by block equation simulation. The SNR is also proportional to the voxel volume, since that determines the number of spins that you're looking at. And finally, some term that's related to the sampling, and we'll look at that more closely here. So for an imaging pulse sequence, if you look at the total time that the analog to digital converter is on, we'll call that T, acquired at a sampling rate characterized by bandwidth BW, the total number of samples n is just T times BW. Now effectively what we do with those n samples is just average them all together. So let's try to calculate the signal-to-noise ratio of that sum. So the signal itself from a particular voxel is some voltage that appears at the terminals of the coil. That voltage is independent of any of the sampling properties. So we'll say for here that that's proportional to some constant. We'll call it 1. The noise voltage is proportional to the square root of the bandwidth, and that's a fundamental property of thermal noise. So let's sum signal and noise across all the n samples. The sum of all the signals is n, and when you sum thermal or incoherent noise, the sum is proportional to the square root of the number times the magnitude of each sample. So substituting in n equals t times bandwidth, we have this expression. The bandwidth falls out of that, so you end up with simply the square root of the total time independent of the bandwidth, and we'll insert that here. Now you might ask whether the voxel volume, or the number of spins in the voxel, contributes to the noise. And while it's certainly true that the noise comes largely from the sample, it turns out that the noise voltage is actually not dependent on the choice of voxel volume. And that's because the noise source is actually not localized to the voxel at all. In fact, the noise voltage is independent of the imaging process entirely, because the noise is thermal noise and not related to the magnetization. So in the end, we end up with this actually very compact and simple expression for SNR in MRI that allows us to compare the SNR of different pulse sequences.